It's been a while since the MasterTech program has been able to bring you information about an entirely new powertrain. Last month, we started to do just that by introducing you to the continuously variable transaxle. Well, this month, we'll continue by introducing you to an all-new family of four-cylinder engines, as well as an all-new controller that has been designed specifically for this application. Hello and welcome to the December MasterTech. We have a significant amount of information to share with you regarding that controller and what's being referred to as the world engine. So let's get started. So you may be asking yourself, what is a world engine? Well, it's the result of a joint venture between Daimler Chrysler, Hyundai, and Mitsubishi. Together, they form the Global Engine Manufacturing Alliance, or GEMA. The world engine is actually a collective name for a family of four-cylinder gasoline engines. They include a 1.8-liter engine that produces 143 horsepower and 124 pound-feet of torque, a 2.0-liter engine that makes 155 horsepower and 139 pound-feet of torque, and a 2.4-liter engine that has 173 horsepower and 164 pound-feet of torque. These three have many parts in common, and you can expect to see these engines in many future products offered by Daimler Chrysler, beginning with the 2007 Dodge Caliber, which will carry the body code PM. Advanced technology makes the world engine highly competitive in both quality and efficiency. The key features that we'll discuss with you today include a high-pressure die-cast aluminum block, a balance shaft module with an integrated oil pump, several select-fit components, direct valve actuation, dual variable valve timing or VVT, and dual thermostats. We'll also discuss new special tools that you should be aware of. Let's begin with the engine block. The all-new world engine actually makes use of two high-pressure die-cast aluminum cylinder block castings. The 1.8-liter and 2.0-liter engines share a common block, while the 2.4-liter engine uses a unique block. Regardless of the displacement, gray iron cylinder liners are cast into every block. Another feature found on every world engine is a cast aluminum structural ladder frame, which bolts to the bottom of the cylinder block. This ladder frame has been designed to increase engine and transmission stiffness. The aluminum ladder frame's function is similar to that of the bed plate used on the existing iron block 2.0-liter engine. However, you'll note that the world engine's ladder frame does not include the main bearing caps. The aluminum frame also includes an integral windage tray. The windage tray is designed to strip the oil off of the crankshaft for reduced friction at high engine speeds. You'll also find that the oil filter mounting is integral to the aluminum ladder frame on the intake side of the engine. The ladder frame is sealed to the block with black engine RTV. When using black engine RTV to reassemble any of the world engines, you need to understand that there are a few locations that call for special attention. These areas are the timing cover, the oil pan, and the cylinder head cover. They all contain T-joints that require forcing the RTV into them to ensure proper sealing. To avoid damage, you should refer to service information for proper engine sealing procedures in these T-joint areas, as well as all other areas in which black engine RTV is used. Now, let's take a look at our next world engine key feature. On 2.0-liter and 2.4-liter world engines, chain-driven dual counter-rotating balance shafts reduce second-order engine vibrations. The oil pump is integral to the balance shaft unit. The 1.8-liter engine does not include balance shafts. However, it does have a chain-driven oil pump. On 2.0-liter and 2.4-liter engines, the oil pump and balance shaft assembly is driven by the crankshaft at twice the speed of the engine. The assembly is bolted to the block below the crankshaft. in a location similar to the balance shaft unit found on the existing 2.4-liter iron block engine. You should note that the balance shaft module and integrated oil pump must be serviced as an assembly only. Let's look at the next key feature of the World engine. All World engines use several select-fit components. These select-fit components provide smooth, quiet engine operation and contribute to engine durability. Pistons, buckets, upper and lower main bearings, connecting rod bearings, and a single cam bearing are all supplied in precisely controlled size increments. Unique markings on every World engine determine the correct size for bearing and piston replacement. The World engine select-fit measurement markings are found in 3 locations. The first location actually has 2 sets of markings in the same place. These are found on the right side of the engine in the center of the block just below the head. The first set of markings indicates the upper main bearing shells. Note that this is the measurement for the upper main bearing shells only. They're indicated by a 1, 2, or 3. The second set of markings in this location indicates the cylinder bore measurement. The cylinder bore marking allows you to select the proper piston size, either A, B, or C. The second select-fit marking location also has 2 sets of markings in the same place. These are found on the nose of the crankshaft. You'll notice that the engine size is also indicated here, but is not considered a select-fit marking. This is for assembly purposes only. The first set of markings indicates the connecting rod journal size. This marking specifies the proper connecting rod bearing size and is indicated by a 1, 2, or 3. The second set of select-fit markings in this location indicates the lower main bearing shell measurement. Note that this is the measurement for the lower main bearing shells only. They're indicated by a 0, 1, 2, 3, or 4. The third and final select-fit marking is located on the front camshaft cap. This location has only one select-fit mark that indicates the exhaust camshaft front bearing shell. The marking specifies the correct exhaust cam bearing size indicated by a 1, 2, or 3. You should use caution when installing the front camshaft cap. Refer to service information for the proper torque specifications and tightening sequence. Next, let's look at the valve system on the World engine. All 3 of the World engines have direct valve actuation that's accomplished by solid steel bucket tappets. This system provides both simplicity and minimized noise levels. The solid buckets are located between the camshaft and the tops of the valves. Because of this direct connection, there is no rocker arm assembly. Proper measurement is critical because if the clearance is too tight, valves can be burned. And if the clearance is too loose, the valve train will be noisy. The buckets come in many different sizes, but you should note that some buckets used in production may not be available for service. One unique feature that you may notice is that the camshaft lobes do not sit directly over the center of the buckets. This is by design, and it's to aid in bucket and valve rotation, as well as to ensure even wear. Unlike other cylinder heads, when servicing a World engine head, you should not invert this head on the bench, unless you have removed the buckets. This is important to understand because the buckets must remain in order. They should not be moved to another location on the head. If the buckets are removed, they must be reinstalled in the same bucket bore. If a camshaft is replaced, all buckets must also be replaced. You should refer to the service information for proper procedures regarding bucket replacement. One last word of caution regarding the World engine head. Extreme care should be taken to avoid scratching the sealing surface when placing the cylinder head on a bench. Although there is no recommended service interval for checking valve clearance, if the valves are noisy, you need to use the procedure in the service information to check the clearance. And that brings us to our next valve system related key feature. Variable valve timing, or VVT, has been around for many years. But the World engine takes full advantage of this technology by using dual VVT. With this system, VVT takes place on both the intake and exhaust camshafts independent of each other. Dual VVT gives the World engine the flexibility to provide peak power and torque with smooth idle and low-speed operation. It also improves fuel economy. Dual VVT uses solenoid-operated oil control valves located in the cylinder head, one for each camshaft. These valves provide pressurized oil to the intake and exhaust camshaft phasers that are fixed to the end of each camshaft. The phasers are mounted between the nose of each camshaft and its driving sprocket. Note that the camshaft sprocket and phasers are serviced as an assembly only. Engine oil pressure is used to alter the angular position or phasing of each camshaft relative to crankshaft rotation. At idle, the cam phasers are in a lock pin position. However, the cam positions will vary as a function of torque demand and engine operating conditions. The new global Powertrain Engine Controller 1, or GPEC1, which we'll discuss later in this program, determines when and how much to index the camshafts. The intake camshaft can be advanced 20 degrees of camshaft rotation. The exhaust camshaft can be retarded 17.5 degrees of camshaft rotation. This results in an increase in valve overlap as well as in power and torque. Camshaft position sensors monitor each camshaft to verify their angular positions. The GPEC1 continuously monitors these sensors to detect if a malfunction within the VVT system occurs. One last item to note regarding the dual VVT system is that any time you remove the cylinder head, you must replace the VVT oil screen. The screen is located in the block inside the left front oil supply passage. Never attempt to clean the VVT oil screen. Replacement is the only option. Now, let's move on to our next World engine key feature. Every World engine uses two thermostats. However, these thermostats are not interchangeable. Similar to other cooling systems, the purpose of the primary thermostat is to regulate coolant temperature in the cylinder head and the engine block. It's distinguished by a dual poppet design, which blocks the coolant bypass when the thermostat is open. It also has a jiggle pin, which makes it easy to identify. The secondary thermostat is designed to regulate coolant temperature in the cylinder block only. This thermostat is identified by its single poppet design and bleed hole. The secondary thermostat does not have a jiggle pin. For coolant flow in the World engine, there are three basic modes of operation. If both thermostats are closed, the coolant system is in full bypass mode. Coolant flows through the bypass where a small amount flows to the block. The majority of the coolant flows to the head and is also directed through the heater core. If the primary thermostat is open and the secondary thermostat closed, coolant is directed from the head to the radiator, where it's cooled and returned to the engine. The secondary thermostat continues to direct coolant back to the block and heater core passages. If the primary and secondary thermostats are both open, the dual poppet design of the primary thermostat allows it to direct coolant from both the head and the block to the radiator, where it's cooled and returned to the engine. You should refer to the service information for proper procedures regarding the dual thermostat system. And that brings us to something that you're going to run into with just about any new engine. As you've probably already guessed, several new special tools are required to properly service the World engine. You should refer to the service information for a complete and up-to-date list of World engine special tools. Now, we've already covered a lot of new material with you about the World engine, but we still need to look at managing engine operation. So in the next segment, we're going to shift our attention to a new engine controller. The all-new World engine gets an all-new engine controller, the Global Powertrain Engine Controller 1, or GPEC1. Let's start with how the GPEC1 powers up. The main relay that sends power to the GPEC1 is located in the secondary PDC, or Power Distribution Center. This separate secondary PDC is located below the left front headlamp assembly. It contains a total of only 3 relays, 1 main relay for GPEC1 and 2 fan relays. If the main relay is removed, all GPEC1 functions cease operation. It cannot communicate at all. There is no direct battery feed which powers up the GPEC1. In the event of a battery disconnect, GPEC1 retains all of its memory, unlike previous PCM-equipped vehicles. However, note that there is a power feed which is separate from the main relay. This is strictly for OBD2 monitors, such as the eSIM, or Evaporative System Integrity Monitor, which will continue to supply the GPEC1 with voltage after the key is turned off. We'll have more information about the fuel management system, specifically the eSIM, later in this program. You'll notice that GPEC1 is smaller and lighter than the NGC currently used with other Chrysler Group engines. And in the manufacturing process, generic software is installed which allows the unit to be built and tested. In the vehicle assembly plant, the GPEC1 is programmed online and customized for individual engines. This customization includes unique items such as the VIN. You should note that service or replacement GPEC1 modules are delivered with the generic software package installed. These modules must be flashed before they're put into service. Now, up to this point, we've provided an overview of the new engine controller. But we also want to describe to you some of the specific systems which GPEC1 monitors and controls. GPEC1 controls and monitors the camshaft positions for the dual VVT system that we talked about earlier in this program. GPEC1 determines when and how much to move the camshafts. The camshaft position sensors, 1 on each cam, are monitored by GPEC1 to detect if a malfunction occurs. Every World engine has an intake manifold flow control valve system. The flow control valve system consists of flaps within each manifold runner that restrict the incoming airflow, making it tumble as it enters the cylinder. Intake airflow tumbling action helps ensure that the fuel and air mix thoroughly and burn faster and more completely. This is done during low-speed, partially open throttle operation when tumbling action would not otherwise occur because the air is flowing too slowly. The flaps are located in the intake manifold just in front of the intake ports. The flaps are mounted on a common shaft that's controlled by an actuator and the GPEC1. Now, you may be wondering exactly what parameters are used to control the intake manifold flow control valve. For the 1.8 and 2.0 liter engine applications, if the engine is operating below 4,000 RPM, the flow control valve will restrict airflow by 35%. When these engines are operating above 4,000 RPM or at wide open throttle, the flow control valve does not restrict airflow. On the 2.4 liter engine, the valve is in the restricted position when the engine is operating below 3,600 RPM. When these engines are operating above 3,600 RPM or at wide open throttle, the flow control valve is in the unrestricted position. Note that these threshold points are not exact. The flow control valve opens at a slightly higher RPM and closes at a slightly lower RPM. This is to prevent constant cycling of the valve. The actuator includes a position sensor located within the motor that's similar to a throttle position sensor. This is to monitor the flow control valve position, either unrestricted or restricted, and alert the GPEC1 if a malfunction occurs. Like other engine controllers, GPEC1 controls the generator output on the World engine. However, GPEC1 monitors charging voltages from 2 locations. It monitors battery voltage and it monitors charging voltage at the generator. If GPEC1 detects a voltage discrepancy between generator and battery voltage, it shuts down the charging circuit. This is a unique feature for GPEC1, as the existing PCMs monitor battery voltage only. GPEC1 does not directly control transmission functions, but it does select the desired gear ratio based on the power demand. As you learned in the November MasterTech program, the low-level detailed control for the continuously variable transaxle is handled by a separate control module. For more details regarding the CVT and how the CVT control module and GPEC1 communicate, refer to the November 2005 MasterTech program. GPEC1 can adjust the displacement of the AC compressor as necessary to provide improved drivability and fuel economy. The variable displacement compressor, or VDC, uses a clutchless compressor design. The shaft is always engaged and the compressor has a swash plate to control the piston stroke. To achieve the desired compressor displacement, GPEC1 sends a pulse width modulated signal to the compressor control valve. The compressor control valve regulates refrigerant flow rate, which determines the swash plate angle. This makes it easy to control compressor power consumption. Note the GPEC1 controls the compressor control valve with a high side pulse width modulated driver. GPEC1 calculates the required compressor displacement by monitoring the AC pressure transducer, the evap temperature sensor, and ambient air temperature. These three inputs go through the totally integrated power module, or TIPM, then to the GPEC1 via the CAN bus system. Based on the bus inputs, GPEC1 decides at what rate to pulse width modulate the AC compressor control valve. As mentioned earlier, one benefit of the VDC system is improved drivability. Here's how this works. With the AC on, the compressor reduces the swash plate angle as demand for AC performance is reduced. As the piston stroke decreases, the torque drag on the engine is reduced. The VDC will also feature a new AC compressor pulley torque limit system. This system is designed to protect the serpentine accessory drive belt in case of a compressor seizure. Here's how the torque limit system works. If the compressor seizes, 3 plastic bridges with limiters break off, freeing the compressor shaft from the pulley. The compressor will not operate, but the pulley will continue to spin. Now, let's take a look at the last GPEC1 controlled system that we want to share with you today. GPEC1 controls the evaporative emission systems on the World engine through the Evaporative System Integrity Monitor, or eSIM. The eSIM is brand new. However, in theory, the eSIM is similar in operation to the Natural Vacuum Leak Detection, or NVLD system, without the solenoid. Within the eSIM housing, 2 check valves, which operate by means of movable weights with a seal at each end, take the place of the solenoid and diaphragm to allow for fresh air intake. One weighted valve is large and the other small. Here's how they work. The large weight check valve inside the eSIM seals for pressure. During refueling, pressure is built up in the evaporative system. When pressure reaches a predetermined level, which is approximately 0.5 inches of water, the large weight check valve unseats and pressure vents to the filter. The small weight check valve inside the eSIM seals for vacuum. When the system cools and the resulting vacuum reaches approximately negative 2.2 inches of water, the small weight is lifted from its seat, which allows fresh air to enter the system, relieving the vacuum condition. The eSIM also has a single diaphragm-operated metal spring-type switch. When the evaporative system is under pressure, the switch is open. However, when a vacuum of approximately negative 0.8 to negative 2.2 inches of water is produced, the diaphragm is pulled inward, pushing on the spring and closing the contacts. When a small amount of pressure is exerted on the spring, it contacts the other terminal, allowing current to flow through the spring, indicating that the switch is closed. The eSIM switch is used for evap system monitors. For a more in-depth description of the operation of the eSIM and the GPEC1, we recommend that you enroll in the DCA training course, World Engine Fuel System Management, Operation and Diagnosis, course code number 0850908. For additional training focused on the World Engine, we recommend that you enroll in the DCA training course, World Engine Operation, Diagnosis, and Repair, course code number 0150508. To enroll, visit the DCA Learning Center website. The site can be reached by selecting the Training tab from the Dealer Connect homepage and then clicking on the DCA Learning Center link. Well, that's all we have to share with you regarding the World Engine and Global Powertrain Engine Controller 1. Be sure to join us next month when we'll be continuing our coverage of the 2007 Dodge Caliber. Thanks for watching.